I welcome all of you to the class. As far as today's class is concerned, today we'll be talking about one more method of solving the nonlinear equations, whether algebraic equations or the transcendental equations. And the method is known as the very important method as far as the um, numerical techniques are concerned, as far as the numerical methods are concerned. This is a very important technique in solving the nonlinear equations. So today we'll be talking about, first of all, this is our lecture number 5. This is lecture 5. And the method that we'll be discussing today is called the Newton-Raphson method. Today we'll be talking about the Newton-Raphson method. Well, as far as the Newton-Raphson method is concerned, let's suppose that we are given a function. We have a function f of x equal to 0. Okay, so we have a single valued function. And we have to solve it. Solve it means, as I have been saying, we have to find the values of x at which the left hand side of the function becomes equal to 0. Fine. How the Newton-Raphson method proceeds is, first of all, let's suppose we plot a graph of this equation. This is x, and say this is f of x. This is f of x. And let's say the graph of the function is arbitrarily, it's say for example like this, nonlinear function. Let's suppose it has a graph like this. Okay, let's suppose this to be the graph of our given function f of x. So this is our function f of x. If you look at the graph, at this value of x, your f of x is equal 0 at this point. And let's suppose the value of x here is, say for example, x naught. Okay, so at this very point, once we plot the graph, okay, at this value of x equal to x naught, the value of our function is equal to 0. Fine. So we say x naught is the solution. So as far as the x naught is concerned, x naught is the solution. Okay, now the question is, as far as the x naught is concerned, we have to find this x naught, but we have to make use of the Newton-Raphson method. What Newton-Raphson method says, it says take an initial approximation. Okay, take an initial approximation, take x1 as an approximate root of the given function. Of the given function f of x, let's suppose that x1 is the solution. Fine. From x1 draw the, at x1 the value of the function is f of x1. Take an initial approximation. So while solving the question using the Newton-Raphson method, we are taking a point x is equal to x1, and we say that the value of the function at x is equal to x1 is f of x1. It is here. Fine. Now, once you have done it, what we have to do, we have to draw a tangent. Okay, at x is equal to x1, at f of x1, that is at this point, draw the tangent, and tangent to this line will be like this. Draw a tangent. Okay, so once we have drawn the tangent at this very point at which the value of our function is f of x1, I mean to say the coordinates of this point will be, along x-axis it is x1, and along y-axis it is f of x1. Okay, so along x-axis it is x1, and along y-axis it is f of x1. Fine. So as far as this point is concerned, as far as this x1 is concerned, at x1, the value of the function is f of x1. At this very point, we are drawing a tangent. And let's suppose this tangent is intersecting our x-axis at another point called x1. Okay, at another point, say for example, x1. Okay, now at x is equal to x1, which is the point of intersection of our tangent with the x-axis, draw find the value of your function. Okay, at x is equal to x1, find the value of your function, that is here. Okay, let me, there is a little error. This cannot be x1, this has to be x2. Okay, let this to be x2. Okay, so first we started with an initial approximation, x is equal to x1, obtained the value of the function as f of x1. Therefore, at this very point, at x is equal to x1, the value of function equal to f of x1, we are drawing a tangent such that the tangent is intersecting our x-axis at x2. Fine. Now at x2, find the value of your function, that is here. Okay. So the value of the function at x is equal to x2 is f of x2. So this is our f of x2. Okay. Now at f of x2, draw one more tangent. Okay. At x2, draw one more tangent. Okay, such that the tangent is now intersecting our x-axis at this point, which we call as x3. Okay, so we will keep on drawing the tangents and finding the points of intersection of this tangent with the x-axis, and this process will keep on going as soon as the value of the point of intersection of the tangent with x-axis becomes equal x naught, and we will stop the iterations and say x naught is our solution. Fine. So as far as the Newton-Raphson method is concerned, we can say the geometric derivation or geometric interpretation of the Newton-Raphson method is all about drawing the tangents. Okay, let me recapitulate the entire process. That is, in Newton-Raphson method, we are given a function f of x is equal to 0, and the question is solve it. We are asked to solve it. Fine. We have to find the values of the x at which the function becomes equal 0. So what we first of all do, I will repeat the geometric interpretation of the Newton-Raphson method. Let me call this as the geometric interpretation of Newton-Raphson method. Okay. So it is like the geometric interpretation is, I'm starting, we will first of all plot the graph, call this as our x-axis, and we state that this is the value of a function f of x. Okay, and let this to be the graph of our function. Okay, our graph of function is like this. Okay, this is the solution point which we have to find. Let's call this as x solution. Okay, so how we proceed? First of all, we have to take an initial approximation. We are taking point x naught as an initial approximation. Okay, and obtaining the value of the function at x is equal to x naught, let that be equal f of x naught. You can take this as x1, obtain the value of function here as f of x1. This is your choice, no problem at all. So at the initial approximation at x naught, the value of the function is f of x naught, and then at this very point, we have to draw the tangent. So once we draw the tangent, okay, and obtain the point of intersection of this tangent with the x-axis and call this as x1. Fine. We'll be calling this point as x1. So we'll keep on drawing the tangents. Okay, we'll keep on drawing the tangents as long as the point of intersection of the tangent with x-axis. We'll keep on drawing the tangents as long as the point of intersection of this tangent becomes very close to this x solution. Okay, so as it gets very close to it, so we will terminate our entire process and we'll say that we have obtained our solution. Okay, now again, if you look at this point, the first tangent that we have drawn, it is intersecting our x-axis at x1. Therefore, we can say if this angle is theta, we can therefore write tan of theta tan of theta is equal perpendicular, that is f of x naught, divided by the base. As far as the base is concerned, that is x naught minus x1. That is x naught minus x1. Okay. And if you look at this tan theta, we know from the definition of the slope of the function, from the definition of slope of a function, we mean the derivative of a function. Okay. So if we are taking the tan of x, tan theta at x is equal to x naught, so it actually means the derivative of a function at x is equal to x naught, which we write as f prime x naught. Okay, this is how we define the slope of a function. Okay, therefore we can write f of x naught is equal f prime x naught multiplied by x naught minus x1. Therefore x1 will become equal x naught minus f of x naught divided by f prime divided by f prime x naught. Okay, so this is how it works. So what we have done, if you look at the value of your x naught is the initial approximation. This is the initial approximation. So with the help of this initial approximation x naught, we have obtained the value of the function as f of x naught. And at f of x naught, we have drawn a tangent that is intersecting our x-axis at x1. So what is the next step? The next step is obtain the value of the function at x is equal to x1. And let's suppose that is equal, that is here, which is f of x1. Okay. At f of x1, draw the tangent. At f of x1, draw the tangent. Okay. Such that the tangent is intersecting at one more point, that's called x2, and keep on iterating this process. Fine. So as we said that x naught is our initial approximation, what does this x1 become? This x1 becomes our next approximation. It becomes our next approximation. Okay. So in Newton-Raphson method, we start with an initial approximation x naught, draw a tangent to obtain the next approximation. At the next approximation, draw the tangent on the function to obtain the corresponding next approximation. So this process keeps on, we keep on repeating the process as soon as the approximation becomes very close to the actual solution. Okay, so this process keeps on repeating, but very important is to understand this equation. Okay, as we stated, this x1 is equal to x naught. X1 is equal, the next approximation is equal to x naught, the initial approximation, minus times the f of x naught, the value of the function at x is equal to x naught, divided by the derivative of the function at x is equal to x naught. Okay, f dash x naught, because we are drawing the tangent at x is equal to x naught. Okay, so we are drawing the tangent at x naught comma f of x naught. So this slope will be for the function where the tangent is drawn at x naught comma f of x naught. That's why we have written it as f prime x naught. Okay, this is the geometrical derivation. So as far as the geometrical derivation or the geometrical interpretation of the Newton-Raphson method is concerned, in the geometrical interpretation, we are saying that x1, the next approximation, is equal to initial approximation minus f of x naught divided by f prime x naught. Okay, this is what the geometrically, how we geometrically define our approximation as. Now we have to keep on going. We have to take the next approximation, that will be in terms of x1. Okay, so next approximation will be x2 is equal x1 minus f of x1 divided by f prime x1. The third approximation will be x3 is equal to x2 minus f of x2 divided by f prime x2. Similarly, this will keep on going. So we can write the next approximation in terms of the general formula. We can write You have here 3, you have here 2. So we can write x of I plus 1, that is xi plus 1th approximation is equal to xith approximation minus f of xi divided by f prime xi. Okay, this is the Newton-Raphson formula for calculating the approximations. Okay, this formula is used by the Newton-Raphson formula, Newton-Raphson approximation, in getting the value of our approximation very close to the x solution. Okay, such that x solution minus xi plus 1th approximation is almost equal to 0. At that time, we can conclude that xi plus I approximation is equal to our x solution. Okay, this is how the method actually works. We can also do it using what we call as the analytical derivation. This is second part we can do by taking analytical derivation. What do you mean by the analytical derivation? As far as the analytical derivation is concerned, we are given a function f of x is equal to 0 and we have to solve it. Okay, so in order to solve the function f of x is equal to 0, we take x naught to be the initial approximation. Let's take x naught to be the initial approximation. Okay, as we take x naught to be the initial approximation, therefore we can simply conclude that f of x naught has to be equal to 0 if we take this as to be initial approximation. Okay, or okay, let me do it in other way. Let me not say f of x is x naught is equal to 0. I will simply conclude that x naught to be the initial approximation. Okay, as I had in the graph, as we had in the graph like this. This was our x naught, but at x naught, the value of our function was not equal to 0. Okay, let me do it like this. F of x naught is not equal to 0. Okay, but we are taking this x naught to be the initial approximation from which we are actually starting our iteration process. Okay, let x naught be the initial approximation. But to this x naught, I have, see, you have your solution here. X solution is here. Okay, x solution is here. X naught is somewhere here. Okay, so there is a difference between x naught and x solution. Okay, so what I have to do, the initial approximation which I am taking as x naught, I have to, this x naught is not my solution. This is not our solution. Why this is not our solution? Because at x naught, the value of our function is not equal to 0. It is x solution at which the value of our function is 0. So it means to x naught, we have to do the correction. There has to be correction to x naught to make x naught approximate to x solution, to approximate it to the x solution. Okay, so there has to be some correction in between. So how we do it? Let me say, let x naught be the initial approximation and let h to be the correction to x naught. Okay, that is this much, as you see here, that is this much. Okay, this much is the correction, and let me call this correction as h. Okay, that is what I have to do is very simple, is by doing what I call as just a minute. Okay, let x naught to be the approximation to h. Okay, so we will say that it is f of x naught plus x h, that's equal 0. Let me recapitulate it, what I am doing, so as not to create a confusion. What we had, we were given a function f of x is equal to 0. We have to solve it. We are starting our approximation with x naught. Okay, we are starting our iteration process with x naught. X naught is not our solution because at our x naught, the function of the value of the function is not equal to 0. So to this x naught, we are adding up a correction factor h. Okay, such that f of x naught plus h is equal to 0. Okay, this h is called the correction factor. This is our correction. Okay. So if we expand f of x naught plus h, if we expand f of x naught plus h, expanding f of x naught plus h by Taylor series expansion, what we will get? By Taylor series expansion, we will get f of x naught plus h is equal, f of x naught plus h by Taylor series expansion will be equal to f of x naught plus h times f prime x naught plus h square by 2 factorial f double prime x naught plus so on plus so on h raised to power n divided by n factorial, okay, f of fn x naught. This is by the Taylor series expansion. Okay, while we perform the Taylor series expansion, we are selecting our correction factor x naught. We're selecting our correction factor h. The correction factor h, the correction factor h and f of n x naught, the nth derivative at x naught, these are selected in such a way such that limit n approaches to infinity, as we have an infinite number of terms, as the number of terms go on increasing, h raised to power n by n factorial f of n x naught approximates or limits to 0. Okay, the value of the correction factor is to be selected in such a way such that as n goes to infinity, the higher order terms in the Taylor series expansion approximate to 0. So as we neglect the higher order terms, neglecting higher order terms in Taylor series expansion, what we will get? F of x naught plus h is equal f of x naught plus h times f first derivative at x naught, and we neglect all the higher order terms because we are selecting our h in such a way that at limit n approach to infinity, the higher order terms approximate to 0. But look here, therefore from this equation we can directly obtain for higher order terms, neglecting them, f of x naught plus h is equal to f of x naught plus h times f prime x naught. But look here, we are saying f of x naught plus h to the initial approximation, we're adding the correction factor h such that f of x naught plus h becomes our solution. That is f of x naught plus h is equal to 0. Therefore, this entire term is equal to 0. Therefore, we can say the correction factor h becomes equal, minus f of x naught divided by f prime x naught. Okay, so what does this mean? So we started our function, if we return back, we started the entire process with the initial approximation as we started the entire process using x naught as an initial approximation. This was our initial approximation. Okay, this was our initial approximation. We started with it. As we went ahead, we said we have to edit some correction, that is h, to make x naught plus h to be our solution. So that becomes equal x naught minus, as h is equal f of x naught divided by f prime x naught. This is what we had obtained using the geometrical derivation as well. So as we started with the initial approximation x naught, as we started with the initial approximation x naught, obtain the value of the function as f of x naught. Okay, we are drawing a tangent at that very point to obtain the next value as x1. And if you recall, your x1 was equal x naught minus f of x naught divided by f prime x naught. This was the geometrical derivation, and our geometrical derivation is, approximating up with what we call as an analytical derivation. So this is how the Newton-Raphson method works. The Newton-Raphson method simply then works with, let me recapitulate the entire process by which the Newton-Raphson method works. So Newton-Raphson method works, whatever function you are given, okay, whatever function we have to solve, first of all, we will start the entire process with an initial approximation. Let's call that as x naught. Okay. Obtain the value of the function at x is equal to x naught. Fine. And what you have to do, we have to draw the tangent at that very point. So as we are drawing the tangent, let me undo the entire process. Okay. So we will draw the tangent. Okay. So as we are drawing the tangent, this tangent has to intersect the x-axis at some very point. Let's call that as x1. At x1, obtain the value of your function, draw one more tangent. Okay, so these tangents, the points of intersection of these tangents gets very, very close to the x solution. So when it gets very close, at that time, you stop the iteration process and take that approximation at that point of intersection of your tangent with the x-axis as your solution point. Okay, and the formula Newton-Raphson method gives is the ith approximation, I plus 1th approximation, becomes equal x ith approximation minus f of x ith divided by f prime x ith. Okay, this is the formula. Now let's solve a question using the Newton-Raphson method to understand how this method actually works. Okay, and what we actually understand by these derivatives and the values of the function. Let's suppose we are given any function. Let's suppose we are given a function y is a function of x is equal to, say, for example, x square plus 4. Let's suppose we are said solve f of x is equal to 0. Solve x square plus 4 equal to 0. So we have to solve this equation using the Newton-Raphson method. This process will be continuing hopefully in the next class. Thank you very much.